Hello everyone. So today we're going to have a look at how can we perform operations on two vectors but given their components. Now that we know how to express vectors in terms of their components in any reference frames, now we're going to leverage that in terms of carrying out our vectorial operation. Because last time we talked about vectorial operation just in terms of vectors. So remember the cross product definition using the right-hand rule, and the definition for the magnitude of the resulting vector, or the dot product, the head-to-tail summation of two vectors. All of these were carried out in terms of just the vectors themselves, in terms of quantifying their magnitude and direction. But today we're going to leverage what we learn about expressing vectors in terms of components to carry out those operations. All right? So that is section 1.2.4. And this is known as vector and its components, or vector component operations. All right, the first one is the addition or summation of two vectors given their x, y, z components. All right, so how can we do that? Well, let's just go back to what we learned last time in terms of expressing vectors in terms of their components in a given reference frame. Okay, so in this section I'm going to do all of the operations assuming that all vectors are expressed in the same reference frame, and that would be reference frame A to do the examples here. Okay, so how can we express vector u in terms of its x, y, z components in reference frame A? Well, easy peasy. Use the vectrix notation. So vectrix A transpose times components of vector u in reference frame A, like that. Remembering that this is a matrix of unit vectors that are used to define reference frame A. And this is a 3x1 column matrix that contains the scalar components of vector v or vector u in reference frame A. So that is the x, y, z components of that particular vector seen in that particular reference frame A. Okay? So this plus vector v expressed in the same reference frame A, like that, and like this. Okay? Well, what I can write down here is that I can take the transpose of the vectrix out of this, like this, then add the components of vector u in reference frame A to the components of vector v in reference frame A, like that. And if you want to further expand that, you can easily do it by remembering that this is a 3x1 matrix plus a 3x1 matrix. That will be uxa, uya, uza, plus vx reference frame A, vya, vza, like that, and close the parenthesis. Or ultimately just say that this is the transpose of the vectrix A times the x components in reference frame A added together, the y components in reference frame A added together, and the z components added together on both vectors, like that. Okay? So that is how you can practically add two vectors given their x, y, z components. You just add the x components together, the y components together, and finally the z components together, and boom, that's your answer. Just don't forget that a vector plus a vector gives you another vector at the end of the day. So if you just give me that as your answer, Well, that's not a vector. That is a matrix 3 by 1 with 3 scalars. So don't forget about the vectrix here to really ensure that what you get is a vector altogether. Okay? So that is how you can add two vectors together. Now we'll have a look at how can we do the dot product operation we saw previously, but this time given the components of vector u and vector v in terms of reference frame A. So dot product. All right, so u dot product with v. Now you know that it's going to give you a scalar at the end of the day, but how can you calculate that scalar given the x, y, z components of each vector? Well, you could very well just take the Euclidean norm of vector u times the Euclidean norm of vector v, figure out the angle with some trigonometry, and then do the cos of that, multiply all of it, and that will be the answer. But instead of doing that, there's another trick. Because you know, we assume here that we know the components of both vectors, you can just write down vector u in terms of its components in reference frame A. Same old, same old. So this dot product with vector v expressed in terms of its components in reference frame A is just going to be vectors A transpose times components of vector v in reference frame A, like that. And here I'm going to use the trick, or not the trick, but the alternative way to write or to express a vector in terms of its components in a particular reference frame, and that is to use the kind of mirrored way of that expression. So I could rewrite this by first writing u, A transpose like that, and then times the vectrix itself, not the transpose, okay? Because this is equivalent to that. Then dot product of vectors A transpose times components of vector v in reference frame A, just like that. And the reason why I'm writing it this way is because I'm going to make use of this operation here, okay? I'm just going to rewrite it by expanding what is a vectrix equal to and what is a transpose of a vectrix equal to, and then do the dot product, okay? So vectrix here is a 3 by 1 with ax vector, ay vector, and az vector, defining the direction of the x, y, z unit vectors, respectively, for reference frame A. Dot product of the transpose of a 3 by 1 is going to be a 1 by 3. Ax vector, ay vector, and az vector, like this. And finally, times that 3 by 1 matrix that contains the x, y, z components of vector v in reference frame A, like that. And now you'll see why I decided to flip the order of these two guys here to write it this way, because here the dot product of this and that is going to be easily dealt with. We're still talking about dot product of u and v, but again, given their components in reference frame A. So I'm going to rewrite this UA transpose. Now this is a 3 by 1 and a 1 by 3. So linear algebra will tell you that you get indeed a 3 by 3 out of that, and times your VA dn. Okay? Now this 3 by 3 matrix is going to be filled, and we saw that earlier in a previous lecture, with 9 entries. And those 9 entries are essentially dot products of AX, 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 AY, AX, AZ, AY, AX, and so on and so on. I'm just gonna write it real quick to complete this. X, AY, 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 Z, AZ, AX, AZ, AY, and finally AZ dot product with AZ. Okay, so that's what I get for the dot product of U and V given their components in reference frame A. Okay. Now, this stays the same. Now, what about this 3x3 matrix? Well, from the previous lecture, hopefully you remember that whenever you have the dot product of a vector with itself, you'll always get 1. And whenever you get a dot product with a vector with another vector which is perpendicular to the other one, well, you're going to get 0. Okay? So this 3x3 matrix is actually 3 ones like that, and a bunch of zeros on the off-diagonal elements times VA. Now this happens to be your identity matrix, 3x3, like that, times VA. And we saw in the previous lecture that when we have an identity matrix that multiplies a 3x1 matrix, all you get at the end of the day is just the matrix itself, 3x1. And boom. And that is the result here. So if you know the components of the first vector in a reference frame A, and you know the components of the second vector in the same reference frame, don't bother trying to measure the different angles between all unit vectors involved and all that. All you have to do is take the components of the first vector, transpose them, multiply that with the components of the second vector, and that will give you the scalar you're looking for the dot product. Okay? Really easy, real quick. So think of that section 1.2.4 as practical ways to easily and rapidly calculate the vectorial operation whenever you have the components of those vectors. Okay? It simplifies your life quite a bit. All right? So now we looked at summation of two vectors given their components. Now that was dot product of two vectors given their components. Next up would be a cross product of two vectors given their components. So how could we approach this? Well, same as before, let's write down the vectorial operation first. So what we want to do here is take the cross product of u vector with v vector given their respective x, y, z components in a common reference frame, which happens to be reference frame A. So first thing you have to do is to write or express the first vector in terms of its components in reference frame A. As per before, just like that. And we said cross product of the second vector, which can also easily be written in terms of its components in reference frame A, just like that. All right, so here I'm going to use the same trick as before. Or in other words, I'm going to flip the order of these two things for the first vector. So I'm going to write it as UA transpose times vectrix A. Then take the cross product with transpose of vectrix times components of vector V in reference frame A, just like that. All right? Now, exactly as per before, I'm going to expand what this vectrix is. So this is a matrix of unit vectors. And this cross product of the transpose of that, so I'm flipping the rows of the columns and write it like this. And finally, with V A like that. Okay, 3 by 1, 1 by 3. I know I'm going to get a 3 by 3 for this inner operation here. So I'm going to prepare a big 3 by 3 matrix times VA at the end. Now this 3 by 3 is going to be filled with 9 entries as per usual, but this time instead of having AX dot product with AX as what we have previously, now we have AX cross product with AX, okay? So just for completeness, I'm going to fill this matrix with a bunch of cross products. And then we will evaluate each of them individually to figure out the 9 entries of this 3 by 3 matrix, okay? AY cross product Z, AZ cross product AX, AZ cross product AY, and AZ cross product with itself. That's what we have. Okay. I'm going to say that this is then equal to UA transpose times my 3 by 3 that I'm about to evaluate times components of the vector V seen in reference frame A, like that. Now, is that the identity matrix? Or is that the same result as what we had for the inner operation when we did the dot product a couple of minutes ago? The answer is no. Because now, AX cross product with itself is not 1. Okay? And for 2 reasons. First reason is that a cross product of 2 vectors doesn't give you a scalar, but it has to give you a vector. Okay? Second reason is that according to the right-hand rule, this, given that the angle between AX and itself is 0, is going to give you the null vector, because the definition of the cross product, if you just look at the magnitude, this is the magnitude of the first vector, which is 1, times the magnitude of the second vector, also 1, times sine of the angle between both vectors. While there's a 0 angle between AX and AX, so sine of 0 is indeed 0. So some of you will be tempted to just write 0 here, but it has to be a vector. Again, cross product gives you a vector. So this is your null vector. All right? And similarly for AY cross product with itself, you're going to get the null vector. And AZ with itself, you're going to get the null vector again. Now for the 6 remaining entries of this matrix, what you have to do is to figure out the direction using the right-hand rule. And to do that, I'm always drawing my little reference frame that obeys the 3 properties we discussed last time. All right? With AZ out of the board. And I'm set up to do the cross product inside the matrix here. So here you have AX cross product AY. And I would highly encourage you to do it at home on your own to make sure that you really have a good understanding of cross products and the right-hand rule. So you have AX cross product with AY gives you then AZ. Like that. AX cross product with AZ gives you minus AY. And here you have AY cross product AZ. So fingers towards AY, rotate towards AZ, which is out of the board, gives you positive AX. Vector like that. And because I've done this millions of times, I know that the result here is going to be minus AZ, AY, and minus AX, okay? And again, verify that on your own at home. Pause this video now and mess with your right hand. Do the cross product on your own and just confirm that you can do it properly, okay? And I don't want any of you to try to sneak out and do the IJK thing and, you know, doing that, notice this. No, no, no. Do it the simpler way, the simple way, and you'll always be right. Okay. Now, I have to play a bit more with that because that's not a useful form that will simplify my life, right? This is still quite complex as it is, and it's not very helpful. So what I'm going to do next is to expand this first guy here, which is a 1 by 3, Q, X, A, U, Y, A, U, Z, A, times this 3 by 3 matrix, with the null vector on the lead diagonal, positive, AZ minus AY, AX, minus AX, positive AY, minus AZ around here. And this one I don't need to expand. Turns out this 1 by 3 times this 3 by 3 can also be rewritten by flipping those two objects together, okay? So, or in other words, the result of this matrix multiplication could also be written by taking what's inside this 3 by 3, putting it into this 1 by 3, and vice versa. Okay, so I'm going to construct a 1 by 3 that contains the 3 unit vectors that were originally in this 3 by 3, and then take those and fill this 3 by 3 matrix with those 3 entries, okay? So if you do that, you're gonna have to write zeros on the main diagonal, minus UZA, UYA, minus UXA, UXA, UZA, minus UYA, and then components of vector V in reference frame A stays the same. Okay, so I know it can be a little bit confusing for you to understand how I went from this times that equal to this times this, but I can leave that to you to verify on your own. Just grab another piece of paper and, you know, carry this multiplication by taking this times this plus this times that, this times that, and so on, and see if that is equal to this, and the answer will be yes. And the reason why I flipped the elements of this with the elements of that is to simplify greatly my life, because now I recognize this object, right? Because this is the transpose of vectors A. Boom. What is this guy equal to? I don't know yet. And times VA. Okay? Turns out that this is a well-known object in linear algebra and spacecraft dynamics modeling, because this is known as a skew symmetric matrix. Okay? And the way you denote that is by using the 3 by 1 matrix way of writing things like that. But that's not a 1 by 3, right? This is a 3 by 3 constructed out of the 3 by 1. And this altogether is known as your skew symmetric matrix that is built from the 3 by 1 column matrix UA. Okay? So whenever you see a skew symmetric matrix, go back here, because that is the definition of a skew symmetric matrix of a 3 by 1 matrix. So essentially, it will always be zeros in the main diagonal, and you're going to fill the other elements with the same order. You're going to take the z component of that 3 by 1 and do minus z for this element. You're going to take the y component and plug it here, minus the x1, minus y, and positive z. It will always be like that. For any skew symmetric matrices, it's always this particular order with which you're going to fill the elements. Okay? Essentially, go back here on top. If you want to evaluate the cross product of two vectors given their components in reference frame A, the answer is going to take the transpose of vectors A times the skew symmetric matrix that you're going to build out of UA. So out of the 3 by 1, you're going to construct the 3 by 3 according to this definition, and then times the 3 by 1 components of vector V in reference frame A. And that is your answer. Okay? Very simple, very straightforward. You're given, again, this. You are given that. And the answer is, first you construct the 3 by 3 skew symmetric based on this. Multiply that with this. And you just write times the transpose of the vector x in front of everything. And that will be your answer. Okay? That is how you can figure out or calculate practically the cross product of two vectors given their components in a common reference frame, which happens to be reference frame A. Okay, next up is some identities that are very important. So column matrix identities. When I say column matrix, I refer to any column matrix. So a matrix that has n rows and one column only. So that has this format. And that could be, whatever matrix you can think of. So if you have a column matrix with one column and X number of entries, what you can do is use any of the identities that are listed in equations 1.41 to 1.47 to help you out carry out the development of any equations you're playing with, okay? I'm not going to list these particular identities because that would take me half an hour, literally. But just keep in mind that those identities exist in the lecture notes. They very well might become useful down the road. There's no need to memorize them on top of your head, but just remember that they exist. So at one point or further down the road, I will probably say, okay, there's an identity for column matrix I'm going to use in this development. That was equation whatever. So, okay, just be aware that they exist in the lecture notes, and they will play a big role eventually. Okay? Japanese green tea. Okay, so that concludes how to perform operations on vectors if you know their x, y, z components in a common reference frame. In this particular section, we had used reference frame A for demonstration purposes, but that could be any reference frames as long as both vectors are expressed in the same reference frame. Now, in section 1.3, we'll have a look at how can we express a vector. Hold on a second, let me rephrase that. How can we transform the components of a vector seen in reference frame A, for example, into another reference frame? So how to go from one reference frame to another reference frame. And the reason why it is so important to do that for spacecraft dynamics and control is that the dynamics formulation of spacecraft can be expressed in a variety of reference frames. You can express the motion in the Earth-centered inertial reference frame that has its origin at the center of the Earth. Or we could express the motion of the spacecraft in another reference frame, this time a reference frame attached to the spacecraft itself, or attached to the center of the Earth again, but this time that rotates as the spacecraft rotates around. So all this to say that spacecraft dynamical formulation involves various reference frames, and it is often useful to know how to transform components from one reference frame up to another reference frame. And to do that, we'll have to involve rotation matrices. And eventually, in a subsequent lecture, we'll also talk about principal rotations. Okay, so let's consider you have reference frame A in red. You have reference frame A that has three orthogonal unit vectors, obviously, denoted by AX, AY, and AZ. You also have another reference frame. Let's call it reference frame B. That also has three unit vectors, but happens to be oriented in a different way than reference frame A. But it's BX unit vector like here, BY over here, and BZ over there. Now what you can do, or what you want to do here to understand the idea behind rotation matrices, is to first find a way to express this particular vector in terms of its components seen from that reference frame. As we did previously, right? We were taking a vector, say U or V, and we have discovered how can we express that particular vector in a given reference frame through the use of the vectrix notation and column matrix of components. But this particular vector here, Bx, can also be written in terms of Ax, Ay, and Az. Similarly, this particular vector, which happens to be a unit vector of another reference frame, still, it is just a vector, can also be expressed in terms of Ax, Ay, Az, and same thing for Bz, right? Bz can be expressed in terms of Ax, Ay, and Az. So that's what we're going to do. So I'm going to use a couple of colors here. I'm going to say that Bx, which is a vector in 3D space, can be equal to, well, let me first write Bx, By, Bz. Then I want to switch colors. Those three vectors can all be expressed in terms of those three other vectors. I'm going to say in terms of Ax plus Ay plus Az. And same for By, we're going to rewrite that vector in terms of Ax, Ay, and Az. And same for Bz. Ay plus something times Az. Okay? Now, the somethings that I've left out in those equations are simply scalars. Or in other words, x, y, z components of that particular vector along Ax, AY, and AZ respectively. Okay, and same here. I have three scalars that are missing that are simply the x, y, z scalar components of that particular vector along those three particular directions, or along AX, AY, and AZ. And same here. Three scalars that are telling me the orientation of BZ with respect to AX, AY, and AZ. Okay? And those scalars that are missing in those parentheses will simply be denoted as CXX. I'm going to remove the parentheses for cleanliness. CXX, CXY, CXZ, CYX, CYY, CYZ. I'm going to call this one CZZ or CZX. That one CZY, and this one CZZ. All right? So essentially, I just did what I did previously in the previous lecture when we first had a look at how can we write down a vector in terms of its x, y, z components the long way, okay? Without involving any vectices or whatnot. Essentially, all I did, again, is to express those three vectors as a linear combination of AX, AY, and AZ. That's all I did. So because this way of writing things is a bit cumbersome, I'm going to group what I have on the left-hand side and what I have on the right-hand side in terms of two objects, okay? I'm going to say, I'm going to concatenate dx, dy, dz as a 3x1 matrix. I'm going to say that this is equal to a 3x3 matrix filled with 9 entries, and those 9 entries will be the scalar components of those vectors in terms of the A unit vectors. That's my CXX, CXY, CXZ, CYX, CYY, CYZ, CZX, CZY, and CZZ. All right? And this is going to be multiplied with the remaining unit vectors on the right-hand side. I'm going to concatenate into a 3x1 matrix. AX, AY, AZ, like that. All right? So those two things are perfectly equivalent. It's just a cleaner way, a more compact way of writing what we had before in terms of matrix operations now. All right? Or, if I'm clever and I remember the definition of a vectrix, I can say that, oh, I remember that. That is actually the vectrix itself. So that is vectrix B, like this, equal to a 3x3 matrix. I'm going to denote as CBA, and you'll understand why in a second, times, well, I know that. This is just vectrix A. So vectrix A, like this, okay? So this 3x3 matrix here plays a fundamental role, okay? Because this matrix contains the scalar components that defines the orientation of those unit vectors with respect to those ones. Or in other words, contains all the information you need to relate the orientation of reference frame B with respect to reference frame A. All right? So because of that, this particular matrix has a particular name, and that name is known as a rotation matrix. Okay? So as you can easily see from that very simple, elegant expression here, the role of a rotation matrix is to define or express the orientation of this particular reference frame, which is mathematically defined through its 3 unit vectors bx, by, bz, with respect to another reference frame, mathematically defined through its ax, ay, az unit vector. Okay? So I'm going to say that the first use of a rotation matrix is to define the orientation of reference frame B with respect to reference frame A, but not the other way around. Okay, the order here is very important, and this is why the subscripts of that rotation matrix notation that we've used C to denote is key. Because here, this is rotation matrix that defines the orientation of reference frame B with respect to reference frame A. So you read left to right, okay? B with respect to A. Reference frame B defined with respect to A here on the right hand side. Define the orientation of B with respect to A. Because if you had, say, the other way around, if you had reference frame A equal to a reference rotation matrix times reference frame B, while the role of that particular rotation matrix here would be to define the orientation of reference frame A with respect to reference frame B. And in that situation, the rotation matrix would be labeled as CAB, okay? As opposed to CBA in that particular example. Okay? So that is the first use of a rotation matrix, or again, to define the orientation of one reference frame with respect to another one. Green tea. Green tea is good. Turns out that rotation matrices in the literature, in some textbooks or journal papers or conference proceedings, are widely referred to as direction cosine matrix. Direction cosine matrix. Why is that? We'll discover that together, okay? So, if you were to take the previous expression, which was matrix B equals C, BA, matrix A. By the way, trick to remember the subscript order, if it's AB or BA. Just look at what you have on the left-hand side. This is B. So here, the first subscript is B on the left-hand side of the subscripts. And on the right-hand side, you have A. So you have the A on the right of the B like that. So B, B, A, everything looks nice, everything is correct. All right, so if you were to take the dot product on both sides of this equation with vectrix A transpose, by the way, the following demonstration is only to explain why a rotation matrix is also referred to as, and I keep looking at the laptop, I should look at the camera, right? Anyway, the reason why we're doing this development is that I want to show you why people call a rotation matrix a direction cosine matrix. So to do that, we are taking the dot product, the transpose of the vectors A on both sides of that equation. Like that. Yeah, let's do it. Let's do it out loud. So if you remember from before, I'm not going to do it again. This is your identity matrix, and a 3 by 3 times the identity matrix gives you the 3 by 3. So this can disappear. So now you have from that last expression that rotation matrix that defines the orientation of B with respect to A is also equal to vectors B dot product transpose of vectors A. And if you were to expand that, here we're going to get dx, dy, dz dot product transpose of vectors A, which is ax, ay, az. 3 by 1, 1 by 3. Surprise, surprise, you get a 3 by 3 filled with dot products between the unit vectors of reference frame B and the unit vectors of reference frame A. So you're going to get bx dot product ax, bx dot product ay, bx dot product az, dy ax, dy ay, dy az, bz ax, bz ay, and finally bz dot product with az, like this. Well, hopefully by now you remember that the definition of the dot product is magnitude of the first one times magnitude of the second one times the cos of the angle between both vectors, right? Well, it turns out all these are unit vectors, so magnitude of the first times magnitude of the second will always give you 1. So essentially, this matrix is just a bunch of cos of 9 different angles. Cos of the angle between bx, ax, and so on, okay? So cos of 9 different angles that are defining the respective orientation of the unit vectors of B, reference frame, with respect to the unit vectors of the reference frame A. So that's what it is. So rotation matrix, CBA, is just a 3 by 3 matrix that can be calculated by taking the cos of the various angles that are defining the orientation of all unit vectors of plane. And this is why people call a rotation matrix a direction cosine matrix, because of all the cos function involved in the calculation of it. Okay? So that was just kind of a side note that explains why rotation matrix is also known as direction cosine matrix, but also give you the opportunity to keep playing with vectors, vectrices, vectors, matrices, dot product, and whatnot, okay? Now, that was for the first use of rotation matrices, and that is to define or express the orientation of one reference frame, say B, with respect to another reference frame, say A. Okay, but there is another use, which is a little bit more practical. So to discover that, we will express vector U in terms of its components in reference frame A. And hopefully you didn't forget how to do it. Do the transpose of vectors A times 3 by 1 matrix filled with x, y, z components of this particular vector measured along ax, ay, az respectively. Okay? But this particular vector can also be expressed in terms of its components in reference frame B. Nothing prevents you from doing that, because the same vector exists regardless of reference frame through which you are measuring or determining its xyz components. Right? So vector u is just vector u, regardless of how many reference frames exist and how many reference frames are you using to figure out the xyz components. Too many markers here. You can have reference frame A, y, is it like that, right? What is different is the x, y, z components of the same vector based on which reference system you're using to measure it, to measure them. But the vector is the same regardless. So here we have expressed u in reference frame A and u in reference frame B, but ultimately u has to be equal to u. Or you could say that then, based on those two facts, vector A transpose times UA has to be equal to vector B transpose times UB. Now, if you take the dot product on both sides with vector B, you're going to get the vector B dot product vector A transpose times UA equal vector B dot product vector B transpose times UB. We saw that several times already, and we know that this is your identity matrix 3 by 3, and we've determined that that's a 3. That identity 3 by 3 times a 3 by 1 gives you just a 3 by 1. And say equal then to UB on the right-hand side. Now here, you have this. Vector B dot product vector A transpose. So if you remember what we did 5-10 minutes ago, you will hopefully remember that this is actually CBA, right? Those two vector C's being dot product with each other gives you CBA times UA. All this is equal to UB. I actually like to write that equation upside down. So UB is CBA times UA. And that is the second use of the rotation matrix, right? Because the first use was to relate, if you remember, vector B to vector A. Or in other words, was to relate or to define or to express the orientation of reference frame B with respect to reference frame A. But now we've discovered the second use of a rotation matrix. And that is to relate not necessarily vector C's between each other, but components of the same vector seen in two different reference frames. And that is the most powerful use of rotation matrices. Okay? That is define components of a given vector. In this example, we've been playing with vector u, but that could be any vector seen in given reference frame, say B, right? Components of u seen or measured from this perspective of reference frame B, with respect to components in another reference frame. Essentially, if you have the components of this vector in reference frame A, or in other words, you have this information available to you, and you know the orientation of reference frame B with respect to reference frame A, or in other words, you also have this rotation matrix available to you. Well, if you want to determine based on those two quantities the components of the same vector but seen in reference frame B, all you have to do is to apply this very simple equation. But again, don't get mixed up, because this particular reference frame based on the subscripts, right, BA, allows you to go or to express the components in B given the components in A, or go from A to B, essentially. You know A, you know this, you want to go to B, well, just multiply these two together. But things can be switched around that easily. You couldn't say that UA is C, BA, UB. That doesn't work. Based on the trick I gave you already for the subscripts of reference or of rotation matrices, the subscripts don't match. You have A and now you have B. As here you have A and B. That doesn't work. So in that case, if you want to go from B to A, or given B, how can you find A? Well, you need to use the proper rotation matrix, which would be CAB, okay? To make sure that the subscripts match on both sides. But turns out that if you know CBA, but you need CAB to perform an operation, you can easily do it, because there is a very interesting property of rotation matrices that tells you that CAB is actually the inverse of CBA. That is an interesting property, yet that is cumbersome, because calculating the inverse of a 3x3 matrix is not fun at all. I'm not sure if you've ever done that by hand, but it is a tedious process. But fortunately for you, the inverse of a rotation matrix is also exactly equal to its transpose. That is so much better. So much better, right? Because now if you need CAB but you have CBA, all you have to do is transpose the matrix. There's no calculations involved. Just flip the rows with the columns, and boom, that is your answer. Okay? So CAB is the same as CBA transpose, and vice versa. You could say that CBA could be obtained from CAB by taking its transpose. Okay? Same as CDE could be obtained from CED with its transpose. So the transpose, think of it as, the effect it has is that it flips the subscripts of the rotation matrix. You had AB, took the transpose, becomes BA. ED, transpose, becomes DE, and so on and so on. So that is a very powerful trick that allows you to quickly find the rotation matrix you need based on what you have, if what you have is not what you need. Okay? All right. The last thing I want to cover for this lecture before we talk about principal rotations in a follow-up lecture, well, the next one, is to talk about another property of rotation matrices that will allow you to do quick calculations, okay? So to do that, let's first go back to our vector u, and let's express that vector u in terms of three different reference frames. So reference frame A, like that. Okay, I'm going to go quicker because by now, hopefully, you understood the concept of expressing a vector in terms of its components in a given reference frame. So it could be written in terms of reference frame A, or it could be written in terms of reference frame B, or that particular vector can also be expressed in terms of any other reference frames, say C, like that, okay? Now, from what we just saw in terms of the second use of rotation matrices, that was to convert the components of a vector from one reference frame to another one, you could say that the components of vector u in C, seen in reference frame C, can be obtained from components of vector u in reference frame A. And again, how can we do it? Well, just use the proper rotation matrix that relates A to C, like that, okay? And again, make sure that the subscripts make sense here. But you can also relate UC to UB, like that, okay? Components in reference frame B, components in reference frame C. The relationship is that rotation matrix or that direction cosine matrix. But you can also say that UB is related to components of vector u in reference frame A through rotation matrix CBA, right? So what you can do is take that and substitute this UB for that one, so that you can write CB times CBA times UA. All right? And now you have UC equal to this and UC equal to that. They better be equal to each other. Otherwise, we have a big problem. So we're going to say, okay, UC equal to UC. Here we have CCA times UA equal to that expression for UC, the longer one, which is CCB times CBA. Don't forget the underline notation because those are all matrices. The C's are 3x3 matrices and the U's are 3x1, obviously, times UA, like that. If you look at both sides, you have UA, so you can cancel those terms out and write CCA, or the rotation matrix that relates the orientation of reference frame C with respect to reference frame A. There's twos of a rotation matrix, or you could say this is a rotation matrix that converts the components from reference frame A to reference frame C. That is also equal to, just by observation, of CCB times CBA. Very powerful result right there, because that shows you that you can concatenate rotation matrices together just by looking at their subscripts, right? You have CB, BA. In other words, go from A to B, and then, well, B to B, and then B to C. Or this is the same thing as saying that you go from A directly to C, right? Essentially, a way that I like to think about it is to cancel out the subscripts that are identical. When you multiply rotation matrices, you have CB, BA, the B's are identical, you can cancel them out, and that leaves you with CCA, like that. And you can concatenate as many rotation matrices as you want, there's no limit to it. Quick example on that. If you're looking for CEA, well, you can say that this is CAD, CBC, CCB, CBA, okay? You can stack them as much as you want. The B's cancel out because they're next to each other. The C's cancel out D's cancel out, and indeed you're left with C, E, A on that side. All right, so that is a very interesting property or trick that you can apply to rotation matrices. I will again ease up the process eventually when we'll get to deriving big equations and involving components in various reference frames. It's going to be a mess. I'm going to make things neat and sharp by using those properties that we talked about today. So that's it for today. Hopefully you've been able to learn something and that you enjoyed the process. See you next time when we're going to talk about principal rotations. See ya.